Welcome to another Leetcode problem. Problem number 127, the infamous word ladder problem. It is one of the hardest problem in Leetcode, widely discussed in internet. Even now you can see close to 200 people online now. It was asked many a times in interviews also. Ironically, this is one of a simple, straightforward algorithmic problem, but it is a hard problem because understanding that it is actually a straightforward algorithmic problem is hard here. Let's go into the problem. Given two words, begin word and end word, and a dictionary word list, return the number of words in the shortest transformation sequence from begin word to end word, or 0 if no such sequence exists. So let's check with the example 1. So they have given begin word as hit and end word is cog, and they have given a word list of heart, dot, dog, lot, log and cog. So the expected output here is 5 because we can create a transformation sequence something like hit to heart to dot, dot to dog and dog to cog, and there are 5 words in this particular sequence. That's why we have to return 5 as an output. So how are we creating the transformation sequence? If you notice, from hit to heart there is only one letter difference. So instead of I there is an O here. So in any two word in the sequence should have not more than one letter difference. So from heart to dot, if you see, instead of H there is a D, and dot to dog, instead of T there is a G. So dog to cog, there is instead of D there is a C, and cog is the last word, the end word they are asking us, and we have reached the sequence. So and all the words in this particular sequence should be from the word list. It should not be from any random word. So from the given begin word, so you have to create such a transformation like this, and we have to reach the end word using only the list given in the word list. And there are some constraints. So the begin word length will be from 1 to 10, and begin word length and end word length will be same, and word list will be 1 to 5000, and word list length, every word in the word list length will be same as the begin word. Begin word, end word and word list consist of lowercase English letters. There are not going to be uppercase letters. We don't need to think about case conversion. And begin word and end word will not be same. Okay, additional advantage for us. And all words in the word list are unique. There are not going to be any repetition. Let's try to understand the example one. So they asked us to, the given begin word is HIT and end word is COG, and the word list is heart, dot, dog, lot and COG. So we need to create the sequence something like HIT to HOT, there is one letter difference here, and HOT to DOT, so one letter difference here, and DOT to DOG, so one letter difference here, and DOG to COG, one letter difference here. So like this we need to create, and there are total 1, 2, 3, 4, 5. So the output should be 5. This is the expectation. First we have to understand here is, this is a graph problem, and we are actually doing a shortest path discovery from the begin word and the end word, and how to form the graph. So there is one relation given, every word having one letter difference. For example, hit and heart are having one letter difference. We can consider them as connected. We can consider there is an edge between them. Similarly, if you take dog, dog has connection to cog also and log also, because there are only one letter difference between these two words. So we can consider this edge, there is an edge between log to dog and dog to cog. Let's try to create a graph like this, and then we will do shortest path finding between the begin word and the end word. If you notice, the begin word is not part of the word list. So when we are creating the graph, we have to account that also. Let's start from the begin word. Let's create a node HIT, and then we will take every node, and then we will see any other node which is directly connected to HIT in the word list. So HOT is connected because there is one letter difference, O and I. So we can create an edge between HIT to HOT. So if you see DOT, no, DOG, no, LOT, no, LOG, COG, no, they have more than one letter difference. So we cannot say there is an edge between HIT to any other word. So now let's take HOT and see what are the other words connected. And DOT, yeah, there is one letter difference, H and D. So let's create a edge with HOT and DOT. Check other words. So HOT and DOG, no. LOT, yes. HOT and LOT, there is one letter difference. So we can create an edge. LOT. And let's see, LOG, no. COG, no. We are at DOT. For DOT, let's try to find any other connected nodes. DOT and DOG are connected, and DOT and LOT are connected. So let's create two nodes, DOG, connect DOT and DOG, and DOT and LOT also will connect again. And DOT is, HOT is over, DOT is over, DOG and LOT is there. Let's start with LOT. LOT has connection to DOT already created. LOT to HOT already created. LOG is new node we have to create. Let's create LOG. And let's create an edge like this. So LOT, no other words are connected. Let's go to DOG, and DOG has connection to LOG and COG. Let's create an edge here and create new node for COG. So let's create COG, connect DOG and COG, connect DOG and LOG. So remaining node is LOG, and LOG has connection to DOG, LOT already is there. So we need to create another connection to COG. Let's create an edge here. So this is the graph we can able to create given the begin word and the word list. Now we need to find all the path to HOT to COG. So we have one path which is having 1, 2, 3, 4, 5. So 5 node path one is there, and there is another path like this, come down and go. So this has 1, 2, 3, 4, 5, 6. So 6 nodes it has, and one more path we can do like this. So 1, 2, 3, 4, 5. So another path with 5 nodes in the list, and another path, how many nodes here? 1, 2, 3, 4, 5, 6, 6. So we have even more path. You can go like this, come and go, then come here. This also will have 1, 2, 3, 4, 5, 6 nodes. But the funda here is, so there are no other path shorter than 5. So there are two paths with 5 nodes in the length. This one and this one. So either 1, 2, 3, 4, 5 or 3, 4, 5. In either way, the shortest path is going to be 5, and the expected answer is we need to send number of nodes in the shortest path. So we don't need to worry about which path we are taking. We just need to return 5. So once you understand this and once you come to this conclusion, almost 75% of the problem is solved. Now, to identify shortest path between two nodes in a given graph is very straightforward. We just need to use BFS. So like in the previous step, we have created the graph. We have come across this particular graph, and now we are going to do BFS in this graph starting from the begin node, the HIT. And we will see when we reach COG, and we will know what is actually the distance, what is the number of nodes in that particular path. So we need to know on which level we are in. So we are going to store that in a variable. So when we are beginning, we are actually at the begin node. So already one node is there. Let's keep one in the level and insert HIT into BFS queue. This is a typical BFS, nothing different. So we are starting the BFS traversal. So what we usually do is we will take this particular BFS node and then we will check whether it is already visited. If it is not visited, we will move it here and then check all its neighbors. That's what we will do, right? So we will move this one from BFS queue to visited nodes, and then we are going to encounter the HIT is neighbors. HIT has only one neighbor, HOT, and we are seeing whether it is visited. No, it is not visited. So we can enqueue that here. So HOT is coming to the BFS queue. So we have visited this particular, we have checked all its neighbors. There are no more neighbors for HIT, and this level is over. We are coming back to the BFS queue. So this time we are updating the level to 1 to 2 because we are checking the first level neighbors. The first level neighbors of HIT are currently in the BFS queue. We are going to take only these nodes currently in BFS queue and traverse them. So any more nodes which are getting added into this particular iteration will not be considered. So again what we are going to do, take this particular node, check whether it is visited. If it is not visited, we will move it here. After moving, we are going to visit all its neighbors. So let's move HOT to visited node. It is visited. So we are seeing its neighbors. There is one neighbor, there is two neighbor. We are checking whether it is in the visited node. Both of them are not in visited node. So bring them to the BFS queue. So enqueue them into BFS queue, DOT and LOT. So at this level we have only one node. We had only one node, and then we visited that node. The other two nodes, dot and lot, which are currently in the BFS queue, are enqueued in this particular level. We are not going to traverse in this particular level. So we are moving to the next level. Update 2 to 3, and in this particular level we have two nodes in the BFS queue. We have to visit both of them. So after visiting these two only, we should go to the next level. So typical BFS, we are checking whether it is in the visited. If it is not visited, move it here and check its neighbors. So let's remove this one from BFS queue and put dot here. After that, let's see what are the neighbors of its node. So one neighbor, two neighbor and three neighbors are there. Heart is already here, so we don't need to worry about heart, but dog and lot are not here, so both lot and dog should come to the BFS queue. So let's update BFS queue using, so let's just change different color because it is current level. So we are going to put dog and lot into the BFS queue. So I'm using different color because these two are entered in this particular level, but this was entered in the previous level itself. We have to traverse this also to complete this particular level. So dog and lot are entered at current level, but one more optimization what we can do here is dot is already here and we are going to visit that. So simply instead of checking only here, we can check whether it is already here. If it is already there, we can ignore that. We don't need to enqueue that because we are going to visit that anyway, which is already there in the BFS queue. We don't need to enqueue that node one more time. We can avoid this particular enqueue also. So what we have done now is we have visited dot, and dot had three neighbors, and among the three neighbors, heart is present in visited and lot is present in BFS queue. Only dog is present in neither. That's why we added dog into the BFS queue and moving on. Now as I told you, we cannot increase the level because this lot was entered in the previous level itself. We have to traverse this one before incrementing this level. So coming back, we are checking whether it is visited. If it is not, we are going to move it here. So move lot here and check its neighbors. So lot has 1, 2, 3 neighbors. Among the three neighbors, heart is present in visited and dot is present in visited. Log is not here and log is not here also. Let's enter log here. And we are at the same, we are at level 3, and all the nodes getting added into the BFS queue at level 3 are going as red. So we are going to add log in red here. So visitation for lot is also complete. So there are no more nodes here which were added in the previous level. So we can go to the next level now. So simply increment the level to 3 to 4. Now we are going to take two more nodes here, dog and log. So move dog here. So let's move dog here and visit the dog. Dog has dot, log, and cog. Cog is the end word. We reach the end word here. Okay, so when we reach the end word, we can immediately return level plus 1 as our distance. This is the logic and it is very simple. So what we do is we create this particular graph and then we just do BFS from the begin word until we reach the end word. So once we reach the end word and we can immediately return the level plus 1 as an answer. If we don't reach the end word at all, it means there is no path from the begin word to the end word. In that case, we can simply return 0. Hope this logic is pretty simple. As I told you, it is not very complex problem. It is a straightforward graph algorithm. You just need to create a graph and do BFS to find the shortest path between the begin word and the end word. There is no hard complex logic here. Let's go for the implementation. So initially we need to construct a graph, but before that we can check an end condition. If the end word is not part of the word list, we can simply return 0. If end word not in word list, return 0 because we cannot able to make a path. And we have to create a graph. I'm going to use adjacency list. Adjacency list initially will set for all nodes in the word list. So the word list may not have begin word. So in that case, let's add one more for the begin word also. Another set initialization. Now we are going to traverse the word list. And for every node in the adjacency list, if both are connected, if is, so though we didn't actually implement the is connected function yet, assume that it is already implemented because it will let you think very clearly when you are writing the program. You can think only in the higher level logic, because when you are thinking about how to form a graph, you should not think how to check whether the nodes are connected. So you compartmentalize your thinking capability. So let's assume this function is existing and call it first. Later we'll think about implementing it. If both are connected, so before even checking if both are connected, we have to check whether we have already created edge for them or not. If node in all of word, we can continue. We don't need to check this. We can simply continue here. Then if it is connected, we are going to create an edge. So we have our graph here in the adjacency list. So let's now implement this connected function. So word 1 and word 2. Let's keep diff as initially 0. So diff is going to count number of characters different across word 1 and word 2. And we know that both word 1 and word 2 are going to have same length because they already mentioned every word in the word list is going to have same length as the begin word. So we can simply assume that for I in range of len of w1, if w1 of I not equal to w2 of I, we are going to simply check if diff is not 0. It means diff has already been incremented. We are going to return false. If diff greater than 0, return false, else increment the diff to 1, and if we come out of this one, return true. You may even think, what if the words are same? If the words are same, we may return true incorrectly, right? But it is already mentioned that the words will be unique. So now we have our graph in the adjacency list. Now we are going to do simply BFS to find the shortest path. So let's create a BFS queue. And let's have visitor set. We'll keep it as a list. And the level is going to be initially 0. And let's just add the begin node into the BFS queue. So now let's traverse the BFS queue until the BFS queue is empty. We are going to increment the level inside the while loop. And at this level, we just need to traverse how many nodes are already in the BFS queue. So if we are going to insert any more nodes into the BFS queue, we should traverse that only in the next level. We have seen that in the walkthrough. So you should remember, we should not traverse any nodes that are getting added into the BFS queue at this iteration. So for that, we are going to have one more for loop, and this for loop will run for the elements which are currently in present. This for loop will not iterate for the newer elements which are going to be added into the BFS queue now. So for underscore in range of len of BFS queue, it is an advantage in Python. So this range of len of BFS queue will be calculated at the beginning of the for loop. So if there are like 3 elements in the BFS queue, this loop will run for only 3 times. So if you are adding any more elements into the BFS queue inside the for loop, that will not be considered for the for loop iteration. Okay, let's pop the node equal to, and let's add it to the visited. Now let's traverse all its neighbors. For nai in of node, if the neighbor is the end node, we can simply return level +1. Else, we have to check whether the neighbor is present in the visited set or in the BFS queue. In that case, we don't need to do any other operation. Otherwise, we have to enqueue that neighbor into the BFS queue. Elif in visited or in BFS queue. In that case, continue. Else BFS queue dot append neighbor. This should be fine. After the while loop, you should return 0, because if there is no actual path between the start word and the end word, we have to return 0. That is one of the constraints. Let's run this with previously selected example cases. Okay, all the cases successful. Let's submit this code and see. Yes, our code is accepted. Please give a thumbs up if you like this video, and don't forget to subscribe to understand hard complex topics easily. Thank you for watching.